What is the difference between methane and water? If you're not a chemist, you might think, well, water is something that we drink, right? It's something that's necessary for life. You have to drink it in order to survive. When you think of methane, you might think of a gas. It's something that we might burn for fuel. You might also know that methane is poisonous, right? It's not something that we consume, whereas water is something that we consume. Now, if we're looking at this from a general chemistry perspective, you can take a closer look at the differences between methane and water. So here, of course, we want to look at the formulas for methane and water. So methane is CH4, water is H2O. Now those formulas tell us a little bit more about the differences between methane and water. Right? So we have carbon here in our methane, represented by the C. And we have oxygen over here in our water, represented by our O. And then, of course, we have hydrogens here in both methane and water. So now, of course, as chemists, we can say one of the differences between methane and water is that they have different elements, either carbon or oxygen. They also have different amounts of hydrogen in them. Now, how does that make them act differently, either as a fuel or as a liquid that we like to drink? Well, to answer that, of course, as again, looking from a general chemistry perspective, we want to take a closer look at what these elements actually are and what is different between them. So, one of the key differences, of course, between elements that we learn in general chemistry is the number of valence electrons. So if we take our carbons, carbons have 4 valence electrons. We know this because they're in group 4A on the periodic table. Our oxygens have 6 valence electrons. And we can draw those valence electrons around our atoms here to represent them as we would in a Lewis diagram. So here's our carbon with our 4 valence electrons, and our oxygen over here with our 6 valence electrons. So this makes for one of our key differences here between our methane and water. Now, of course, we can use these valence electrons, and as we know from general chemistry, these will be used to form covalent bonds that will link our molecules here together. So we take our electrons, and we're going to share them together with our other atoms here, our hydrogens, for both the methane and our water. Again, we need to remember that the key rule here is our octet rule. Meaning that our atoms want to fill their outer layer of electrons. That outer electron shell. And for most of our atoms, they do this by gaining 8 total electrons. So we want our atoms to have 8 electrons overall, and they do this by sharing electrons with other atoms within our molecule. So for our carbon, it's going to bond together with 4 hydrogens. So we bring in our 4 hydrogens. Each of these hydrogens has a single valence electron, represented by my dots next to my H's. These single valence electrons will be shared with single valence electrons from our carbons to make covalent bonds. So there's my first covalent bond formed between my carbon and hydrogen. And of course, each of my other hydrogens can share an electron with our carbon. Electron from our hydrogen and our electron from the carbon combined together. We have two electrons joining together in each of these covalent bonds. Overall, now my carbon has 8 electrons surrounding it. Right, so I have the 2 electrons from each of my covalent bonds. 2 plus 2 plus 2 plus 2 equals my 8 total electrons, fulfilling my octet rule. If I go over here to my oxygen for my water molecule, so my oxygen will do the same as my carbon. I can take my hydrogens, and I want to share electrons with my oxygen in order to fulfill the octet rule and fill up that outer electron shell for my oxygen. I share these 2 electrons between each of my hydrogens and my oxygen. Now again, note that my oxygen has 2 electrons in each of these covalent bonds. I also have these what we call lone pairs of electrons, these non-bonding electrons. There are 2 of these lone pairs, each with 2 electrons. Again, I have 8 electrons total for that full outer shell of electrons for my oxygen. So one of the key differences between my methane and my water is that I have a different number of valence electrons on my carbon and oxygen, and so they form different numbers of bonds with hydrogens in order to fulfill that octet rule. I end up forming 2 bonds with my oxygen to get to 8 valence electrons and my full octet. I end up forming 4 bonds with my carbon, so I have 8 total shared valence electrons around my carbon, and both of them have their octets fulfilled. Now this, of course, explains why we have these formulas here, but it still doesn't really tell us a whole lot about why we have this difference in terms of the behavior of these chemicals. Right? One being something that we drink, one being something that we burn as fuel. Now, as we move on from this sort of general chemistry perspective of how things are bonded together, in organic chemistry, we're going to be looking at these sort of molecules, but we want to take a deeper look and look at how these molecules behave and how we can start to predict the reactivity of these molecules. Now, in order to understand that reactivity and the behavior of our molecules, we need to review one of our key principles from general chemistry, which is electronegativity. Electronegativity is one of the key factors that will determine the reactivity and behavior of our molecules. As you may remember, electronegativity is defined as the ability of an atom to attract the shared electrons in a covalent bond. Right? So when we look at these covalent bonds that we drew here for our methane and our water, we need to note that these electrons here aren't necessarily going to be equally shared in these bonds between our atoms. Right? So our atoms are essentially pulling on those electrons, and the strength of that pull relates to the electronegativity of our atoms. If you have a more electronegative atom, it's going to pull those electrons closer towards itself and away from that less electronegative atom. Now, of course, we need to understand how our atoms will differ in electronegativity. And this is a periodic table trend, meaning that it just changes as we move around the periodic table. So as we move to the right on the periodic table, we're going to be moving towards atoms with higher numbers of protons. Right? So the number of protons increases. So We increase the number of protons, and so of course that gives us a larger positive charge, and that then will increase the pull that we have towards those negatively charged electrons, since of course negative charges are attracted towards positive charges. So moving right on the periodic table will increase our electronegativity. The only exception to this is our far right column, the noble gases. They don't really have any pull towards those electrons because they already have that full outer electron shell, that full octet of electrons. Now the other factor that will affect this is the size of our atom. As we move up on the periodic table, the size of our atoms decreases, and as the size of our atom decreases, that means that our outer electrons are going to be closer to the nucleus, and so they'll again feel a stronger attraction or a stronger pull towards that atom that's smaller and has that nucleus closer to the outer electrons. So we're decreasing our atomic size, and that results again in an increase in electronegativity. So our electronegativity will increase as we move to the right on the periodic table and as we move up the periodic table. Our most electronegative atoms will be up in the top right corner of the periodic table. These will be things like fluorine, oxygen, and nitrogen are some of our more electronegative atoms that we'll encounter in organic chemistry. So now, of course, we have this concept of electronegativity where our atoms are pulling those electrons towards them. How does that affect our molecules here, right? So that makes methane different from water, but how does it make it different? So if we look at our electronegativity, so carbon and hydrogen are actually fairly close in electronegativity. So carbon is to the right of hydrogen, but it's also down on the periodic table compared to hydrogen. So their electronegativities are relatively close, and so these electrons are roughly equally shared. Now, with our oxygen, so as I just said, oxygen is one of our more electronegative atoms. It's far to the right on the periodic table, which means it has a lot of protons with their positive charge pulling these negatively charged electrons in our bonds towards that oxygen. So we can actually draw little arrows here showing those electrons getting pulled towards our oxygen. We use these little arrows with a plus sign at one end indicating that our electrons are getting pulled away, and so as we move those negative charges closer towards our oxygen, that means that our hydrogens become more positively charged and our oxygen becomes more negatively charged. So our negatively charged electrons are pulled towards our oxygen to make that more negative, and our hydrogens then become more positive because they're losing some of those electrons. These little Greek letter delta signs here just indicate these are small charges, right? So our electrons are still being shared between our atoms. It's not like oxygen has taken all of those electrons. It's just that it pulled them a little bit closer towards our oxygen. So it has a little bit of a larger share of those electrons than our hydrogens do. So in methane, we have an equal sharing of electrons. In our water, we have an unequal sharing of our electrons. We also refer to this as polarity. So our water is a polar molecule, whereas our methane is nonpolar. And this creates one of the key differences between methane and water. Now, what this does for our molecules here, again, is it creates this different distribution of our electrons, right? Where we have slightly more electrons around our oxygen and less electrons around our hydrogens, as that oxygen is just tugging on those electrons and pulling it towards our oxygen. Now, one of the key things to note, right, is that all of our bonds here are formed from electrons. So when we're looking at reactivity, we really need to think about electron movement, right? So reactivity is determined based on electron movement. And our electrons are more likely to move around if we have areas with lots of electron density and areas with less electron density. When we have a polar molecule like our water, we have those electrons getting pulled towards our oxygen. So we're going to have higher electron density, we'd say. And those electrons then are getting pulled away from our hydrogens. So these hydrogens give us an area of lower electron density. Now, since our electrons are going to be what we'll use to make new bonds, when we have an area of high electron density, that becomes an area of our molecule that can share electrons, right? There's a lot of electrons that can move around and move to someplace else to create a reaction. We have areas of lower electron density that can take extra electrons and form new bonds. So it's actually these differences in the distribution of our electrons that will be key for determining the overall reactivity of our molecule. So our water becomes much more reactive since it has this difference in its electron distribution, whereas our methane is relatively unreactive because our electrons are just kind of equally shared. There's no area where we have lots of electrons that we can give away. There's no area where we have very little electrons that we'd then be looking to accept electrons. That extra reactivity allows us to do a lot of different reactions, which are key for the biological role of water. Now, because these differences in electron density are so important, we use specific names for these in organic chemistry. So an area of high electron density is going to be called a nucleophile. So this word just literally means that it's nucleus loving, right? Phile is the Greek word for love. Nucleo, of course, just refers to the nucleus. So what this is saying is that since we have lots of electrons here, we want to find another nucleus that we can bond, that we can interact with, that we can react with in order to form a new chemical bond. When we have low electron density, we want to gain more electrons. So we want more electrons to flow into this area where we have low electron density. So we refer to this as an electrophile. So that's an electrophile or an electrophilic site. Electrons want to move towards sites of low electron density, or our electrophiles, and they want to move away from our nucleophiles. Right? So nucleophiles are often going to be moving electrons over to electrophiles in a lot of our different organic reactions. So these two key concepts then will determine a lot of our reactivity in organic compounds. So together, these make up some of our key differences here between our methane and water. Right? So we have different numbers of valence electrons. Our 4 valence electrons with carbon that created our 4 bonds to hydrogens. Our 6 valence electrons with oxygen that then created our 2 covalent bonds here to get our 8 overall electrons for our water. The other key difference is in our electronegativity, right? So our oxygen is to the right and up on the periodic table. That makes it very electronegative. So we created this area of high electron density, a nucleophilic site, and we created these areas of low electron density, or these electrophilic sites. This makes our water more reactive, and it makes it more useful in our living system. Once we start to understand these concepts of electronegativity and nucleophiles and electrophiles, then we'll be able to predict exactly how these reactions might occur for water that we're going to use in our living systems. And that essentially is what organic chemistry is focused on, is learning that reactivity and the behavior of our molecules based on these differences in electron density.